Hi Chem students. Today we will be talking about electrons in atoms. Please get out your notes and something to write with. First, we will talk about the wave nature of light. Light travels through space as a wave. Waves have three primary characteristics: wavelength, frequency, and speed. Wavelength is the distance between two consecutive crests, maximum values, or troughs, minimum values. Wavelength is measured in meters, and the symbol for it is the Greek letter lambda. Frequency is the number of wave cycles, successive crests or troughs that pass a given point per unit of time. Frequency is measured in cycles per second, or hertz. The symbol for it is the letter F. In this diagram, it shows a high-frequency radio waves versus low-frequency radio waves. Speed is a constant for all forms of light. It has a value of 3 × 10⁸ meter per second. The symbol for that is the lowercase c. Now we will talk about the electromagnetic spectrum. Although we often think of light as the energy that enables us to see, visible light is a very small portion of what is called the electromagnetic spectrum. The electromagnetic spectrum, EM, includes all of the characteristic wavelengths of electromagnetic radiation that are emitted by an object, molecule, or atom. The EM spectrum includes gamma rays, which are emitted during nuclear reactions, X-rays, which are used to detect broken bones, ultraviolet, or UV, used in tanning beds, and forensic scientists use them to detect blood and other bodily fluids at a crime scene. Visible. Our eyes detect light in the visible light range. We see colors when certain wavelengths are reflected off of an object. If all the colors are reflected, the object appears to be white. If all the colors are absorbed, the object appears to be black. Infrared radiation, IR, emitted by heat lamps to help keep reptiles and other animals warm, and by your TV remote control. Certain types of thermal imaging devices capture infrared radiation emitted by objects, so you can see them at night. Microwaves, used to heat food and drinks. Radio waves, carry the songs and information we listen to on the radio. The number of the radio station refers to the frequency of the wave. To remember the order of the EM spectrum from longest to shortest wavelength, opposite of the diagram above, use the saying, "Riding much in vans uses extra gas." The frequency and speed of light are related by this formula, C equals lambda F, which stands for speed of light is equal to wavelength times frequency. Wavelength and frequency are inversely proportional. As one increases, the other decreases, and vice versa. Now we will discuss the particle nature of light. Not all properties of light can be explained by the wave model. Max Planck, bottom left, and Albert Einstein, bottom right, refined our understanding of light to include its particle nature. Light can be described as a stream of particles, or bundles of energy, called photons. The details of the particle nature of light will not be investigated in this class. We will only highlight the relationship between the energy of light and its frequency. The equation relating energy of photons to frequency is energy of photon is equal to Planck's constant times frequency. Planck's constant is represented by the h in the equation. The h has a value of 6.626 times 10 to the negative 34 joules second. Energy and frequency are directly proportional. As frequency increases, energy also increases. Long wavelengths, which have a low frequency, also have a low amount of energy. The low energy end of the spectrum includes radio waves, microwaves, and infrared radiation. Electromagnetic radiation with short wavelengths have high frequencies and have a higher amount of energy, which is why they can cause significant damage to our skin and DNA. The high energy end of the EM spectrum includes UV light, X-rays, and gamma rays. According to the particle nature of light, when light acts as a particle, it can transfer all of its energy to another particle, such as an electron. All atoms absorb and emit light when excited by electricity or heat. Elements emit light in unique, distinct patterns called emission spectra. Spectra corresponds to the movement of electrons between energy levels. Spectra are like fingerprints that can be used to identify an element, which we will see in the upcoming flame test lab. In this diagram, it is illustrated how electrons behave when they are excited to higher energy level. Imagine if the source of energy in this diagram is coming from the sun. The incoming photon is then absorbed by the atom. The electron gets excited and moved to the higher energy level. This is called absorption. Emission is what happens when the same electron drops down back to its original state. It will emit a photon. The point to take away from this is photons of light are emitted as an electron drops back to its ground state after being excited. That's it for the notes today. You will not have any homework to go with this video.